have two in a row. Today it's a pleasure to host Evren Samur here. Evren is actually, he's one of our own, I would say. He has the Haptics and Robotics Lab and is an associate professor in the of mechanical engineering at Boğaziçi University. He's also the R&D director at HKTM, a robotics company specializing in motion control technologies. He received his PhD in robotics from EPFL, Switzerland in 2010. His PhD thesis was awarded as the best PhD thesis of 2010 by the Euro-Haptics Society. He was a postdoctoral fellow at Northwestern University in 2011 and a Fulbright visiting professor at Boston University in 2021. His research interests include soft robotics, medical robotics, industrial robotics, marine robotics, collaborative robots, robotic grippers, and haptics. Without further ado, I'd like to leave the stage to him.
Thank you very much, Erol Hocam. It's a great pleasure to be here. So I'm going to talk about a research project which is about a growing soft robot, but I'm excited because if I give you some brief bio, I graduated from Middle East Technical University in 2003 from Mechanical Engineering Department. Then I moved to Koç University, and at that point I started to work on haptics with Çağatay Başdoğan. And then I moved to Switzerland and I did my PhD on, again, haptic interface evaluation and some medical robotics. After having my PhD, I went to Northwestern Medical School in Chicago, and I worked on robotic prosthetic hands. So we worked on how to give haptic feedback to prosthetic users. And then I came back to Turkey. I'm an associate professor now at Boğaziçi University. And last year I was, 2 years ago, sorry, I was visiting Boston for my sabbatical. So very short information about my lab. So we work on novel robotic and mechatronic systems. So our main field is mechatronics. So we deal with hardware and their control, and of course related software programming with those mechatronic systems. And we really work with industrial partners and sometimes medical partners for the application of those robotic and mechatronic systems. Currently, 4 PhD students and 5 master students, and most of them are working on soft robotics these days. I would like to talk about also our project called ROYAL, Robotik ve Yapay Akıl Laboratuvarları, because this is the sister of ROMER. So we were funded in 2019 as well, and there are 20 faculty members involved in this project. The idea is, again, bringing together all those robotics and AI labs from different departments, including engineering, social science, and education. And we will also have our centralized labs. So we will basically increase the collaboration among the partners. And I thank Erol Hocam and Mert Hocam that they gave me a tour today to ROMER, and this is really nice to see all those developments. Hope we will have the same at Boğaziçi University. Okay, so in our lab, some of the past projects are related to haptic technology. So we developed tactile feedback systems for touch screens, basically. And also we work with industrial partners, and we develop robotic grippers to take 2 objects simultaneously, which are coming randomly. So you have to do some computer vision and also develop a dedicated gripper. As I said, another project that related to industrial robotics is developing augmented reality-based safety system for industrial robots, so that you can implement that so industrial robots become fenceless, so it's safe to interact with them like you do with the collaborative robots. And that was a project with the company HKTM. We also work with ETH Zurich Rehabilitation Engineering Lab, and we developed a system, an environment recognition system that can be integrated into exoskeletons, so that the exoskeleton users who cannot walk without those systems can use this environment recognition system to facilitate the control of those robotic systems. So these are some sample past projects. I am going to today focus on soft robotics, and I'm going to explain our growing soft robot, and our intended application was endoscopy. So that's why I'm going to talk about endoscopy, colonoscopy a little bit, and also soft robotics, just to give you an idea what I mean by soft robotics. So as you all know, a typical robot that you come across are made of rigid components like metals or hard plastics. But of course, if you are interacting with humans, then safety requirements force you to use safer materials like soft materials, so that if there's a physical interaction between the human and the robot, then the results are not detrimental. So robots that are made of soft and flexible materials like silicon, plastic, rubber, or fabric are called soft robots, and it's a very trendy topic these days because these robots have the ability to adapt to the environment, so they can change their shape and adapt very well to the environment. So why do we need them? Because they are light, flexible, they can change their shape, and they can interact with the environment. So that makes them safer and versatile to use in regions like medical robots, rehabilitation, human-robot interaction, search and rescue, etc. If you look at the literature, there are totally soft robots, but there are also rigid robots with some flexible elements, and you can develop robotic and mechatronic systems somewhere in between these two. And here are some examples. For instance, recently, researchers developed magnetic machines. So the magnetic field, those soft materials change their shape, and you can use this changing shape to actuate a pump, or you can use it to deliver a drug inside the body. So miniature magnetic machines is a promising subtopic of soft actuators, basically. Historically, hydraulic elastomers, pneumatic tubes, shape memory alloys, pneumatic actuators are used a lot. And you can also use electrostatic actuators to develop soft actuators. So you can embed those actuators inside the soft robot. Here are some examples, some recent examples. One promising area is robotic surgery, because I mean, you all know Da Vinci robot. It's a rigid robot, but used a lot for laparoscopy. But although the wrist mechanism of the Da Vinci robot is great, still they don't have enough mobility because they are rigid. So if you can make a soft robot that have higher mobility, higher dexterity, then of course that will be really beneficial for the patient. Because if you imagine you are traveling inside the veins, for instance, to do some fine surgery, if you have soft robots, that will be really beneficial for the patient. You can also develop wearable robots, like for the hand exoskeletons for physical therapy. Instead of rigid interaction with the human body, those soft interactions will accelerate the recovery of the patient during the physical rehabilitation process because of their compliant nature. Here are some examples. I'm sure you have seen some of the videos here. I can show you this one. So it says Kirigami robotic gripper that you can use to grasp delicate objects. I hope this will work. Okay, anyways, maybe the internet, because of the internet problems. But the robotic grippers are becoming softer and softer because you would like to manipulate any objects, any delicate object as well, like fruits or fragile eggs, for instance. So if you can develop a gripper that is not made of rigid elements, you can achieve those manipulations. Okay, now we are coming to growing robots. So it is a subdomain of soft robotics. So as name implies, they grow. So basically the length of the robot changes extremely. It's not like elongation of a balloon. It's like from centimeters to meters. So like the Stanford researchers, Elliot House and his colleague, developed those kind of robots using the immersion technique. So they developed this prototype that can be used for search and rescue operations because you can make this robot pass through narrow openings and reach areas no other robot can reach. So now this brings us to soft robots for colonoscopy. So let me explain what colonoscopy is. So it is a procedure to screen colon, right? And to perform minor endoscopic procedures inside the colon. So like you can remove the polyp, or you can do biopsies to investigate the tissue, or you can just visualize inside the colon. So it is considered to be the gold standard to detect colorectal cancer. So it is recommended if you're older than 40 years old. And because colorectal cancer is the third most common cancer and has second highest mortality rate among all cancer types in the world. So this procedure is really important and it is performed routinely every year with many patients. So the problems with the current colonoscopy procedure is that the endoscopist pushes the colonoscope inside the colon. So he or she provides physical effort and they stand up during whole operation. The duration of the operation is like 25 minutes, 30 minutes, but it can take up to 60 minutes. In extreme cases, it can be longer than that. And of course, during this time, 25% of the patients feel pain due to mechanical forcing, but there's also psychological distress that makes the patient irritated from the operation. So that's why if we can improve those three items in the current colonoscopy operation, the patients and the operators will benefit. So our goal was to reduce the procedure time and effort to increase the procedure quality and patient safety. So the solution is robotic colonoscopy. So we thought about that, okay, instead of operator pushing the endoscope inside the colon, what if we have a robot that will grow inside the colon, take the shape of the colon, if it is pneumatically actuated, and if we can control its navigation in 3D, then we can have safer and faster operations. So for that purpose, we developed this robotic solution, as you can see in this image, the concept. And I'm going to talk about the details in a minute, but it is controlled by a human operator sitting next to the patient. So teleoperation is used to control the speed and the position of the robot inside the column. So just a background information. So I came up with this idea when I was in London at the Hamlin Symposium on Medical Robotics. So I love going to conferences because you came up with great ideas there. Changing your location and your current work is really light some ideas, basically. In 2013, I came up with this idea, and then we applied, we filed a patent. Prior to date, you can see it's early 2015. At that time, we didn't know about the growing robot, so Elliot Hawks and his colleagues didn't came up that idea, but they came up with a better idea, and now the growing robot is a really an interesting area of soft robotics and growing a lot. Okay, here is our growing soft robot. So basically, the working principle of our growing robot is based on what we call hinge roller drive. So basically, there is a flexible tubing. This image, you can see that white balloon, white tubing. And this flexible tubing is passing in between two rollers, two bearings, basically. And the slack section of the tubing is wrapped around the spool. So when you provide pressure inside the tubing, and if you release the spool, then the rollers, the base is moved forward. And if you pull back the spool, the slack section, if you pull back the slack section while reducing the pressure, you pull back your robot. So that's the idea of our growing soft robot. As I said, it's different than the Hawks growing robot, which is based on inversion, and I think that's a very clever idea. But their problem is that it's one-dimensional. Here, if you use 3 of those hinge roller drivers, so interference, you can see on the left-hand side, and you can control the growing and the orientation of your robot in 3 dimensions. If you look at closely the tubings, there were some problems. Of course, we had to deal with that. So we tried different materials, off-the-shelf tubing. It didn't work, so we had to work with a tubing company in the UK, and they developed a composite tubing for us, where there's flexible inner layer to avoid leakage, and there is a harder outside layer which prevents radial elongation. In this video, you can see how it works. So you release the tubings, release the spool, at the same time elongates. You can control its direction by releasing the slack section different. And with this, you can carry the weight of the robot itself, and you can position the robot in 3D space. We use the haptic device. You can see here Omega 7 to control it. There was a camera at the tip of the robot, so you can get the image in front of the robot. Of course, we have some mechatronics hardware like air compressor, pressure valves, and then control hub to control the release of the slack section of the tubings. So finally, we got this prototype, and here you can see some tests, like how we can lift the weights, how we can position the robot in 3D. So everything is controlled with a teleoperation using a haptic interface, basically. In this open field navigation, so the user is directing the robot to the goal point. And the control behind the teleoperation is straightforward. So basically, we use the position input is fed back to the robot as extension speed for translation, for elongation, but we use the rotation of the haptic device to control the rotation of the orientation of the tip of the robot. So we developed several prototypes. So it took 3 years to get to the final version. With the 1D prototype, we did some tubing testing. With the 2D, we proved the concept, and we improved the 2D prototype, and we performed some navigation tests. And finally, we developed 3D prototypes, two of them large scale. And finally, we developed a small scale prototype, which is the outer dimension is 15 millimeter, and the length of the robot is 1.8 meters. So it is comparable to a classical colonoscope. So that was the ultimate goal, to replace endoscope, the clinical endoscope, with our robot. So we get to that size. So we had all these tubings, but unfortunately, navigation testing in 3D didn't result in what we expected. So we still need to do some improvements to be able to obtain a clinical prototype. But we did some tests with the large scale version, which has an outer diameter of 40 millimeters and a length of 1 meter. So we did navigation tests, and also we did main navigation, and we measured the reaction forces to compare it with the clinical colonoscope. So I can show you some results here. As you can see here, in this maze, the wall reaction forces are less than 1 Newton. But if you look at the literature, like conventional colonoscopes, the forces can go up to 10 Newtons, 15 Newtons. So with a robot, of course, I mean, of course, this is a lab testing. The others are from real operations, but at least we showed that we can navigate in a maze without forcing too much the walls of the test maze. As I said, so we are still working on it. So we need to work on the validation tests of the small scale prototype, and then if we can validate our prototype, then we can continue with the clinical trials. That is still ongoing, but we also looking for other areas that we can use this growing soft robots. One application area could be inspection of structures, like for aerospace applications, or for pipe inspection in the energy sector, or this could also be used for search and rescue operations for earthquake victims, basically. Okay, so I would like to acknowledge my collaborators and my students. So all these prototypes are developed by students, PhD students, and master students. But of course, we collaborated with Boğaziçi University Biomedical Engineering Department and also Acıbadem University Medical School. And we had a partner from medical industry. And this project was funded by TÜBİTAK 5 years ago. And I'm really happy that we obtained a prototype that works fine, and hopefully we will move to the clinical stage. I would like to conclude my talk with a breaking news, basically. So as I said, I'm also the director of the HKTM company. So last year we submitted a proposal to Horizon Europe, and project is funded. And we signed the grant agreement, so everything is going well. So by January 1st, we will start a new project called Safe, Healthy, and Environmental Ship Recycling. So HKTM will be the coordinator of these 16 companies and universities all over Europe. And our goal is to really use robots in the ship recycling areas. Like Aliya, I'm sure you know Aliya. There are ships coming to Aliya, and the end-of-life ships are cut into pieces, and their material, their steel material recycled. So this is an important procedure, but it is done manually. Right now, workers climb onto those ships and they cut it by hand. We would like to introduce robots to this procedure. Of course, there will be some identification parts, so the robots will travel inside and outside of the ship to identify if there's any harmful or other dangerous material inside the ship, so that the cutting can be planned accordingly. We will use mobile robots, crawling robots, and other types of mobile robots to perform the cutting teleoperatedly, so remotely. And there will be some AI components to make this procedure semi-autonomous, basically. So planning will be somehow autonomous. And our goal is really to make an impact on the lives of the workers, their safety and health, and also prevent any contamination to the environment, to the sea, during this operation. Okay, with this breaking news, I would like to conclude my talk, and I would be happy to answer your questions.